100 lecture podcast series. I'm your instructor, Brian Krause, and today we're going to discuss atmospheric disturbances, but more specifically, the types of air masses and weather fronts. So in this mini lecture, like all the mini lectures so far, I'm not going to cover all the topics or ideas that are presented in your text. Rather, my aim is to highlight a few key ideas and then discuss them in a bit more detail. In this lecture podcast, I've included concept checks in the form of these non-graded quizzes at the end. When you get to the quiz slide, you can right-click the mouse and select Pause, which will pause the narrated PowerPoint. And this will allow you time to answer the question. And once you've answered the question, right-click the mouse and select Resume, which will restart the PowerPoint. The following slide will provide then the correct answer and an explanation as to why that's the correct answer. If you're watching this as a video, then you do not need to do this right-clicking. You can just use the controls at the bottom of the video. On that note, let's jump. The learning outcomes for this lecture podcast are the following. Describe the conditions favorable for an air mass source region. Describe the characteristics of and locate the source regions for an Arctic, continental polar, maritime polar, maritime tropical, continental tropical, and equatorial air masses. Explain how air masses are modified when they leave their source region. Describe the characteristic of fronts. And identify cold, warm, stationary, and occluded fronts from a weather map. So before we discuss air masses, we should discuss weather. And weather is the day-to-day state of the atmosphere. So the weather, for example, of the humid tropics is very similar throughout the year, as there's a constant flow of energy that keeps temperatures uniformly high. However, the daily weather is quite variable in the mid-latitudes. Here, these large air masses collide to create powerful storms systems that affect global heating distribution and our daily livelihood. So in this chapter, we'll examine weather systems at a variety of geographic scales that affect our daily lives. So air masses are just an extremely large body of air whose temperature and humidity are fairly similar in any horizontal direction at any given altitude. For an air mass to be distinguishable, it must meet three requirements. First, an air mass must be more than 1,000 miles across and a mile or so deep. Two, it must be uniform in properties in the horizontal dimension, which means that it is physical characteristics such as temperature, humidity, and stability are relatively homogeneous. And three, it must be distinguished from the surrounding air and move as one and retain its original characteristics. So air masses are born in a source region where they take on the characteristic temperature and moisture content. Source regions are often regions of low relief and calm winds that prevent any turbulent mixing and allow the air to take on the condition of the surface over which it forms. So examples of source regions include the icy continental portion of Canada in the winter. As a giant parcel of air moves over this source region, the air will acquire the characteristics of the underlying surface. In this case, the air will be dry, continental, and will be mild to cold, polar, creating a continental polar air mass. So in general, a source region covers several million square miles, and the condition of the surface of the earth are nearly homogeneous. For example, the ocean is a common source region for the formation of air masses. Air will remain over the ocean for a period of time sufficient enough to alter the properties of that air parcel. As an air mass stays over a region, it will acquire the properties of the land or ocean region. For instance, in the above example, the air over the ocean would become moist, providing it remains in the same general location for an extended period. Uniformity within the air mass is reached in anywhere from several days to several weeks. So Table 1 in your text provides a nice outline of the source region properties. Here in this slide, I'd like to discuss the 6 different types of air masses and give a little characteristics of those air masses. The first is the continental polar. And this air mass has low dew points, cold temperatures, and a high degree of stability. Precipitation in association with cold continental polar air is usually light due to the dryness and low moisture capacity of the air. Continental polar air modifies rapidly as it moves to the south. The dew points remain low, but the temperature of the air mass increases when moving south due to the following: warmer soil temperatures, a shallower air mass, and high sun angles, and a lack of surface snow cover. Second, the maritime tropical. The maritime tropical air mass is often felt east of the Rockies. In winter, this air mass is pushed toward the equator, but in summer, it can cover much of the U.S. east of the Rockies. This air mass results from the warm waters of the Gulf of Mexico and the Gulf Stream. The warm waters in this region evaporate an enormous volume of water. Cold water currents tend to stabilize the atmosphere and produce little evaporation, while warm waters destabilize the atmosphere and add moisture. The warm waters and a low level of atmosphere, the temperatures in this air mass warm to the highs in the 80s and 90s in the summer, and the 70s and 80s in the winter. And the majority of the U.S. thunder activity develops within the maritime tropical air mass. As the maritime tropical air mass moves over land, it begins to pick up characteristics of a continental climate. This is particularly true when the maritime tropical air mass moves towards the north. The maritime tropical air mass modifies due to the lower sun angle, drier and cooler land below. Next is the maritime polar. This source region for the maritime polar air is over the cold ocean currents or high latitude ocean waters. This air does not have the moisture content as a maritime tropical air. Since maritime polar air is always near saturation, orographic lifting of the air mass can produce widespread rain or snow. An excellent example of this is the coastal region of Oregon and Washington. This air mass is notorious for producing fog, drizzle, cloudy weather, and long-lasting light to moderate rain. The temperature of a maritime polar air ranges from just above freezing to below 70 degrees Fahrenheit. And maritime polar air is modified as it moves over elevated terrain. On the windward side of a mountain range, maritime polar air can produce an abundance of rain and snow, as I just mentioned. Once on the lee side of the mountain, the maritime polar air mass modifies into a continental air mass. And these air masses produce cold fronts, but the air is not as cold as a polar or Arctic front, and they are often termed Pacific fronts. Next is the continental tropic, or continental tropical. The source region for continental tropical air is the desert southwest, the high plains, and Mexico. However, because the source region is not extensive, continental tropical is relatively unimportant in North America. Arctic. The source region for an Arctic area is the northern Canada. It has the same characteristics as polar air, except it is colder with an even lower dew point. This air often forms when a high pressure area becomes nearly stationary over eastern Alaska and the Yukon. Due to near lack of winter solar radiation, abundant surface snow or ice cover, and a continuous emission of radiation from the Earth's surface, their air will progressively become colder and colder, and temperatures can reach between minus 30 degrees Fahrenheit to minus 60 degrees Fahrenheit. And the last is equatorial, and it only affects North America in association with hurricanes. So that is the 6 different types of air masses that pertain to the United States, or the Pacific or the Northwest. So now let's turn our attention to weather fronts. When unlike air masses meet, they do not mix easily. Instead, a boundary zone called a front develops between them, as shown here in this figure. As we'll discuss, fronts are three-dimensional features. They are not only a boundary between contrasting air masses running along the Earth's surface, but extend upward into the troposphere. And there are 4 types of weather fronts we will be discussing in the following slides: cold, warm, stationary, and occluded fronts. The cold front occurs when a rapidly moving cold air mass, which is shown in this figure moving from the left to the right of your screen, runs into and overtakes a slowly moving warm air mass. It's important to note cold fronts move faster than warm fronts. Because cold air is denser than warm air, the cold air mass remains close to the ground and sinks under the less dense warm air mass. So as the warm air mass rises above the cold air, the warm air begins to cool. It soon chills to the temperature at which water vapor in the air condenses into droplets of liquid water, and towering cumulus and cumulonimbus clouds form from the drops of water produced by the rapid rise of warm air. Because cold fronts move quickly, they can cause abrupt weather changes. Strong winds and severe thunderstorms are often associated with cold fronts. If there is enough water vapor in the warm air, heavy rain or snow may fall. But if the warm air contains little water vapor, the cold front may be accompanied only by cloudy skies. A cold front is portrayed on a weather map as a line of blue triangles pointing in the direction towards which the front is moving. And you can see those blue triangles pointing towards the right, indicating that the cold front is moving from left to right. So here we're looking at a warm front that is traveling from the left to the right. The first difference you might notice between a cold front and a warm front is that the slope of a warm front is generally more gentle. As the warm air rises over the retreating cold air, it cools adiabatically, usually resulting in clouds and precipitation. Because the frontal uplift is very gradual, clouds form slowly, and there is not much turbulence. If the warm air is humid, showers and light rain fall along the front where the warm air and cold air meet. Because warm fronts move more slowly than cold fronts, the weather may be rainy or foggy for several days. Finally, a warm front is portrayed on a weather map as a line of red semicircles pointing in the direction in which the front is moving. And we can see that here in this illustration as well, with the circles pointing towards the right. This weather map is showing us a mid-latitude cyclone with a cold front here on the left. It's bringing down cold air from Canada. In the upper right, you'll see the warm air mass traveling in the northwest direction. And the reason why it is traveling like this is because low pressure systems go in a counterclockwise direction. Here at the bottom edge of the cold front, you can see this long green band, which signifies rain. Remember, as warm air rises over cold air, clouds of precipitation often form. So here in this satellite image is of a mid-latitude cyclone that's moving in from the Pacific Ocean and is about to bring precipitation to much of the west coast. So you should be able to look at this mid-latitude cyclone and note where the leading edge of the cold front and warm front is located, where precipitation would be occurring as well. Sometimes a cold and warm air mass meet, but neither one of them has enough force to move or displace the other. The two air masses face each other in a standoff. In this case, the front is referred to as a stationary front. It is difficult for meteorologists to predict the weather along a stationary front, though it is often resembles that of a warm front. Winds blowing parallel to the front instead of perpendicular can help it to stay in place, as illustrated in the figure on the lower right. A stationary front may stay put for days. If the wind direction changes, the front will start to move again, becoming either a cold or warm front, or the front may break apart completely. On a weather map, a stationary front is shown as an alternating red semicircle and blue triangle. And the blue triangles point in the one direction and the red semicircles point in the opposite direction, signifying that it's not moving anywhere. Here we have two weather maps. In the upper left weather map, we can see a stationary front that's spanning from the corner of Texas all the way through the Great Lakes. And in the lower right precipitation map, we can see the stationary front is producing some light rain. So the next type of front is an occluded front, and this often occurs in the later stages of a storm's life cycle. As the cold and warm front come closer and closer together, the warm sector at the ground, which is illustrated here in the bottom figure, is increasingly displaced, and it's forcing more and more warm air aloft, which can be seen in the top figure, where you can see the warm air mass rising above the colder air mass. When the cold front catches up with the warm front, warm air is no longer in contact with the Earth's surface and an occluded front is formed. And this process usually results in a short period of intense precipitation and wind until eventually all the warm sector is forced aloft. On a weather map, like the one at the bottom, an occluded front looks like a purple line with half triangles and half semicircles, pointing in the direction that the front is moving. For the occluded front, you can think of as the cold and warm front zipping together. It ends in a low pressure area, shown here with a large L on the map, and at the other end connects to a cold and warm front. So here on this weather map, we can see the occlusion that has taken place. And just below this occlusion, we can see where we have a cold front just about to catch the warm front. And they're going to come and zip together, and it's going to extend this occluded front further to the south. So that concludes this lecture podcast on atmospheric disturbances. The remaining slides are non-graded quizzes.